Hello everyone. Probably we'll start. Okay, so are there any questions to the previous lectures? Well, if no, let me remind what we already had. So we had some local operators. Mm. And in particular, there were some special operators among them, which corresponded to some continuous homomorphic symmetries, like current, which is I defy for the free boson, or integer momentum tensor, which is 1/2 GFZ normally ordered. And we also found that we kind of observed that this happens, that if you multiply some operators, fz b of w, we get some series a, b, n of w over z minus w to power n from minus infinity to some n. It was just an observation. So we could compute this for the free boson theory, for example. And today I want to tell why it is actually rigorous and why it is specific for conformal field theory. So topic is Hilbert space. Operator of state correspondence. Vertex operator algebra. So let us think about our theory of free boson, which is put, well, in principle, we can put it on onto some homogeneous surface. Maybe let us do it like this. Some surface, probably with some punctures. So with some surface of genus G with n punctures. So there is our bosonic field, which is from this Riemann surface with functions to real numbers, and we want to compute Gaussian integral dphi e to minus s of phi, and times some operators which are placed in this O1 and so on, On. Some operators which are sitting in these points. So it's some number. Partition function times this correlator. But now let us imagine that we not just integrate over this bosonic field in any point of this Riemann surface, but we cut it with some lines. Maybe let me draw some simpler example. So one of the examples, so it's for some big genus, and one example is like this. So just a sphere, and there are some operators sitting in some points. And here is 0 and infinity. So it is CP1 minus Z1 and so on Zn. So we can, in principle, cut this sphere into pieces, into some pieces. And when I tell that we cut it, for example, we can and we cut this one in some natural way, like this. And when I say that we cut it, I mean that now we want to separate the two integrations over the field which is on this which is on this cuts. So let us denote it somehow. I didn't think about the notation. Maybe let us just call it by the names. So I'm saying that this integral over dphi equals to the product of two integrals. It is an integral over boundary values times the integral over dphi with boundary values fixed. Times e to minus s of phi times all these operators. So this is a partition function times product of times the correlator. And now what happens? Since our action was of this form, integral or defined bar phi, it was only a second order differential operator. So if we fix boundary, how to say it, if you fix boundary values on of some component of this Riemann surface, then a integral with this boundary values fixed does not depend on the other disconnected components, because it's like in one dimension, quantum mechanics. If you have integrals over trajectories and we fix on this value and this value, then integral over integral, so in this part of integral over trajectories between these 2 points does not know about the value of function in this point, for example. So it depends only on the internal. Because, for example, if we fix boundary values for a Laplace operator, then a solution of the equation, like Laplace of phi equals to something, is unique. It's another explanation. So the point is that this
in principle, it doesn't need to be a second order operator. It can be whatever that gives me a well-posed classical problem.
But well-posed classical problem such that boundary value problem makes sense. For example, if you write some higher order differential operator, then you will need to fix. Yeah, you will need to specify all higher derivatives. So in that case, probably we should reformulate this problem such that there are some extra fields corresponding to derivatives, and finally there is some collection of fields that it is enough to specify only their values on the boundaries, so that the problem is well posed. So. It's integral over the boundary values, and this is the integral with yes, yes. So in the case of Laplace operator, it's easy to see in this way. So discretized form of the action looks like S of phi equal to sum of phi I j, phi I j plus 1 plus sum of phi I j phi I plus 1 plus 1 j. So there are links only, there are only such links in the action. So if you now this link and this link. And if you now imagine this field living on the integer lattice, oh, sorry, I should should not connect this point. So let us imagine the integer lattice where this field lives. It can be on a torus, it can be on the real plane. But the point is that if we fix, so if we fix the value of this phi, for example, in these points, uh, like this, we have two domains, like d1, d2, and their boundary dd. So in this case, we have a statement that s of phi equals to let us say that it is sd of 5. Sd of 5 equals to s d1 and boundary values of phi plus s d2 boundary values of phi Oh, and in principle, in this case, well, depending on how we divide this terms between different parts, we can write it just like this sum. So maybe we can also how to write it better. So we have SD, which depends on phi in the domain D, and we can split it as a function of phi d1 and phi dd plus a function of phi d2 phi dd. And if we now substitute it to the path integral, then we can compute these integrals in phi. Oh, actually, I put not enough points. Sorry, I didn't pay attention to this. There was no internal points in this domain, so probably let's choose this one. Oh, it's a bit stupid. So there's a point with internal points. There's a domain with internal points. Maybe even more internal points. So we can say, oh, probably let us let us better say that this CGN is a union of C case some let us call them boundaries. So these are pieces CGN, and these are boundaries. So these are CKs, and these are BMs. So we can write that this correlator equals to it equals to a integral over phi on this BMs product of on the union of BMs, and then a product over all these pieces of Riemann surface of the integrals define such that phi on the boundary on this C fixed. So it's S. It depends on S of this CK. So it depends probably on boundary values and some operators. So these operators belong to their own pieces of the Riemann surface when we cut it. So so we obtained the product of such objects. Each of them depends on the boundary values of phi. So now what is the Hilbert space and what are the objects acting on this Hilbert space? So Hilbert space is Hilbert space is the space of functionals on the boundary values. And we can write some examples of the vectors in this Hilbert space. So check the coordinates on. Let us call it H. So we can we can do something very simple. For example, just take a disk and say that well, there is a boundary value. Uh, so there is this S1, and uh, so let us say that okay, let us take this disk or a cap. It is the same. We have this S1 in this disk, and we can compute. So this is psi, which is a function of phi. This phi is a function from S1 to well, in this case, it will be to real numbers, but in principle, it can be some complex function. So, oh no, sorry. What can I say? So it's a function on this boundary, and we can compute, we can write this function of phi, maybe phi b, or better to say, which equals to the integral over d phi e to minus s of phi, and this is the integral with boundary conditions phi on the boundary of d equals to phi boundary. So this is a wave function. It is one example. Another example that we can put some operator on this disk. For example, here on the tip, or we can put several operators, or one or two. So such objects naturally appear if you start to cut the Riemann surface. Okay, better to draw it like this. So there are examples of pieces of this Riemann surface which contain operators. And here, so here it's actually a vacuum wave function because there are no operators. Here we can construct this other state, psi 1 or 2 of again phi b. It equal to the path integral with the same boundary conditions, phi of dd equals to phi b, but now with two operators, or 1 or 2. Oh, and so on. So you see here we have a correspondence from operators to states. So in this procedure, like we put some operators on a disk and compute a path integral, and compute this functional is a correspondence from states to operators. From operators to states. And it works in arbitrary field theory, so it can be done always. But now we can ask how to go in the opposite direction. Yes, but all of them are isomorphic because all the boundaries are S1s. Was it the question, or what was it?
No. For example, the disk with S1 is just the left side of the CP1 example.
Oh, like this.
But
Yes.
if we want all the CP1, on which boundaries do we have to pick?
No, but what do you mean? So there are some there are examples where there are several boundaries, of course. They will correspond to multilinear operators on H. Mm. Mm. It was that a simplest example. Mm. Mm. So what did they want to do? So now we want to go in the opposite direction. We want to construct states starting from the operators. So from states to operators. So mm, we remember that in the CFT we have conformal symmetry, and in particular, in particular, uh, uh, mm, uh, how to say it, L0 and a scaling transformation. And if we want to insert some state as the operator, we do the following. So let us consider maybe this Riemann surface. Mm. And make it much bigger than we want. Maybe let us better take the Riemann sphere for simplicity, because in this case it will be easier to describe this kind of complex moduli. So let us put here some points. Let us rescale them from the very beginning. RZ1, RZ2, so on RZN, and put here some disk. So we have some operators which are kind of actual operators, O2, On. And we put here some boundary values and we cut here on some hole, and this is the functional of the boundary values of phi. There is some phi b. So we take this partition function and integrate it with psi depending on phi b. And let it be of radius 1. So now we can use conformal transformation to move all these points to positions z1 and zn, and it can be written like integral this z1, zn, and here this circle becomes very small. It becomes of size 1 over r. Psi of phi b d phi b. So it is something which lives in a very close, like, let us say that it is 0, and here it is at 0. So we have something which lives in a very close vicinity of point 0. So the subject should be expanded as a series of local operators inserted in this point. So it is sum over some p's, some operator of 0 or 1 or n. So the moral of the story is that if you have
I've not understood, but on the left-hand side down there, isn't the whole picture equal to psi of phi? Or not understood?
no, I'm saying that so what I'm doing here is how to insert state psi into some point. How to insert psi as the operator. So
would you like to add like this cut to your inner surface?
yes, so we can draw a picture that psi, this is a kind of empty cup which corresponds to a vacuum state, but we can draw some other object which is a kind of filled cup, and we put here some letter psi big on this filled cup. We say that it is some state in this Hilbert space. So it's kind. This means that we how to insert psi. This means that we take this Riemann surface and glue to it this cup. So so this whole integral equals to kind of this object. So this equals to this sphere with the hole, and here we glue this field cup on this boundary. And the statement is that it's a combination of some local operators, because we can shrink the boundary of this of mm, of the circle to zero. Some of course there is partition function here. Right. And if we now want to derive OP, then it is so. So here we had the correspondence from operators to states. We can just compute the boundary values, and we can also insert a state and expand it as a combination of local operators. And we can now try to do this procedure forth and then back. So we can derive OP. So what we do? We take a disk with two operators. Let this be B and let this be A. This disk equals to some wave function psi AB. And then we can say that this psi AB is expanded over the over a combination of some other operators sitting in the center of this disk. OP. And now looking at the left-hand side and the right-hand side, we see that it is precisely the OP, that product of two operators in some points equals to a linear combination of operators in the center, and the center corresponds to position of this second operator of B. So is it fine? So, and but if you work with massive theory, we cannot do this because we don't have scaling transformation. So in principle, I know that people write some operator expansions, but probably it's correct to say that in that case they are asymptotic series, and here they're just Laurent series, which are convergent. Okay. Well, actually, at this moment, the
So how does the scaling variance impact the convergence of the series you are mentioning?
we know that A and B have positive have some dimensions. So this A times fz times b of w is some abn of w, and dimension of this field is delta of delta A, delta B. For this field, it is delta A plus delta B plus n. Plus n or minus n. Yeah, because here we have z minus w to power n. Yes, so first we know that this series should truncate at some n, because we will see later that unitarity restrictions say that unitarity says that dimensions of all fields should be greater or equal than 0. And why the series is convergent is because so let me think. Oh, we should say what it means precisely that it is convergent, and because these operators make sense only if they are considered under the correlation functions with something else. So convergence of this series depends on what else we consider here. So we should write, we should draw pictures like this. And there is some point z. There is some point w, there is some point z, and singularities in z. So maybe I would better put w equals to 0 for simplicity. So here is 0, here is z, and we are considering this correlator with a of z, b of 0, and some other fields, O1 and so on, On. Singularities so of z1 and zn. So singularities of this correlator appear at 0 and all these points z1 and zn. And as we know from the complex analysis, the radius of convergence of a function is defined by a position of the first singularity. Well, it is one series, so it has singularity at 0, and we are interested in other singularities. So a radius of convergence is a minimum of this absolute values of z1 and so on the. So if you don't put other operators directly to zero, then this correlator will converge in some domain depending on the other operators. So is it okay? But in massive theory, we cannot fix this the dependence. We'll have some function which depends on mass scale and uh, mm, mm, and hmm?
For example, the propagator of a massive theory in the input provided is like massless.
Yes. So let me think. Yeah, but so we can write this series assuming mm, well, in a kind of conformal limit when this theory looks like a conformal one. But I don't know any precise statement about the status of this operator expansions in massive theories. Mm. So so by the way, to this moment, there was some ambiguity because I was calling operators the local observables, which can be put at some point, maybe. And now we can say that if we take so. Um, yes. So now we want to construct the actual operators which act on the Hilbert space. Local observable. Two operators on H. It is easy. We just take the following piece of CP1 and put here O. So it is so there's phi B1, there's phi B2, and the subject lives. So it is. We can call it some VO, and this object lives in H in times H, which is the same as H times H star. So it is a operator on H. So mm. Yes. So what we have now, that mm, the space of states and the space of operators are actually isomorphic, and uh, uh, before we were studying the action of some components of energy momentum tensor, or mm, of the current on the space of operators, but at the same time we can consider their action on the space of states. So let me check. Uh,
So in some sense, depending on the orientation that we give to our research surface, is an element of H plus the dual of H.
yes. Yeah. So of course the orientations should be matched correctly, but it is more or less clear. I think. Okay. So. Mm, what? Probably I can erase this. By the way, concern about the vertex operator algebra. So people also uh, mm, mm, take this picture as a motivation for the exams. So there is a notion of vertex operator algebra. Mm. Which consists of a Hilbert space. So there are some other requirements, but basically it consists of the Hilbert space and also of the operator of this of the following object. Uh, uh, y of which acts from the Hilbert space to uh, operators on the Hilbert space times a formal series of z. So which probably don't remember precisely which precise space of series we should write here to make this to make everything rigorous. But the idea is that we have this space H, which is at the same time space of operators and a space of states, and we can write this operator of insertion of the local operator, like we can write y of some v when v goes to when v is in H, and this looks like this in this language, that we take this sphere. Maybe let us better draw it as let us also act with this on some vector also in H. So we get some vector in H which depends on Z, and the value of this is the following. We take a disk and we put here states W at 0, or operator corresponding to this space. We take a point Z and insert here the state V. Maybe it's hard to see it here. So it is point 0, and here is a state V. Oh, V at 0. And here is point Z, and we inserted oh, sorry, it was double. And here at this point Z, we inserted state V, and we got some vector in the Hilbert space which lives on the boundary. So, or in other words, we can say that this is axiomatization of the fact that we can construct an operator acting on the Hilbert space from any element of this Hilbert space, which is at the same time the space of operators for co-observables. So. So there are some axioms of this vertex operator algebra which I don't want to write. But for example, saying it in words, one axiom is that there exists operator product of such operators, and it terminates at some finite order. And another axiom that there is an energy-momentum tensor, which corresponds to the two-identity operator in this Hilbert space. So. Yes.
So it's from H cross C into an H times the volume.
Yes. And also people who work with operator algebras like not OPs of operators which contain such poles. They prefer to use they prefer to compute commutators of formal series, and in that case they contain delta functions. For some reason they like it more. Okay, so there is such a thing, but let us now talk about the action of this operators on the space of states. Well, I already raised this picture. Mm. So, for example, you want to compute some object uh, like this. Uh, some O n minus 1 of Zn minus 1, some O1 of Z1, and O0 of 0. You want to try to write it as a product of some operators. And so how shall we do this? Let us draw a picture. Namely, there is point 0, where this operator O0 lives. There is some point Z1, and so on. And somewhere there is a point Z the n, no, somewhere there is point R. So now let us try to cut this sphere by the equidistant circles. And say that the Hilbert space of our interest lives on such circles. So this object should equal to the product of some states, and the first state is precisely the state created by the operator dimension delta 0. It sits at the origin. So the state which will live on this kind of smallest circle, or better to say at 0, will equal to delta 0. Then we have some product of operators which correspond to annuals. And we should somehow understand what is the meaning of such operator. Namely, so let me think. No, let us for the moment say that there are operators which correspond to this anyway with points zi inside, and denote them as operators O1 of z1 and so on, O n of zn. So O n minus 1 and minus 1 of zn minus 1. And here there's a vacuum at infinity, and here there's operator O n of r. So O1 of the one corresponds to this object. It equals to O1 of the one. So now I want to move this last operator O n of r to infinity, or in other words, to find which state is created by this operator when it goes to infinity. So how shall we do this? Let us say that product of these operators equals to some zero or n of r times sum of some functions of the I of the i's operator valid functions acting on states delta p. And so this is the two-point function, because here we reduced everything to the operators which sit at 0, and it equals so it equals to delta of this delta n and delta p divided by r to power 2 to delta n. which means that for any state, such a correlator, when R is big, behaves like 1 over R to power 2 delta n. So there is an example of this operator state correspondence. So we can now say that if we send R to infinity and multiply this O of R by R to delta n, it will equal to some state at infinity. So mm, mm, yeah, very good. So we can say that O delta n of infinity maybe maybe uh, maybe better to say like this, that state delta n equals to the limit of mm, up to infinity uh, 0 O delta n of R times R to 2 delta. So in this way we get vectors in the dual space. Uh, so is it okay? Yeah, and by the way, this this a choice of circles where the Hilbert space will live is called radial quantization. Mm. Hmm? Ah, yes, it is also possible. Yeah, maybe it's even better explanation that if we perform z to minus z transformation, then we get the correlator of the same kind, but with O n of r sitting around 0, and then we can just move it to 0. Yes. Mm. But, hmm?
What is the vacuum in this graphical representation? Just a point.
Uh, well, it's empty. So if we imagine that it is a sphere, that it is an empty cup at infinity, empty cap at infinity, because so the picture should be like this. Here is 0, here is infinity, and vacuum corresponds to the vector in the Hilbert space where there is nothing at infinity. And this is a vacuum. Right? Mm. No, there is no boundary in this case. We say that everything lives on the complex sphere, and there is a regularity condition for this phi at infinity that it should not diverge.
This is for the graph, but for the cat, like if I use that instead of one vector space.
So which one? This one?
Top left of the other vector.
Mhm. Which one? Mhm.
Where you go by vectors and use graph.
This one?
Yes.
Yeah.
So if I want a vacuum in that format, it would amount to fix the phi be 0, 1.
No, just compute. So you're asking what it means precisely for the boundary conditions at infinity. Mm, mm. Well, I think that if this circle is located far away from everything, really at infinity, then we should choose a condition like phi equals to 0. But I'm not I'm not quite sure. If we take it of finite radius, then this wave function corresponding to this vacuum should equal to the path integral with some boundary conditions. So and we can actually compute this function. So if you want explicit representation of this vacuum of this vacuum state as functional on the Hilbert space. So probably I can erase this, right? So what we want to compute? We want to compute a path integral with let us choose some radius r. And that phi of phi of mm, so let us say that it has an expansion uh, as a power series. Phi of r e to the I theta. Like this. So this path integral will equal to some determinant times which does not depend on phi's times e to the action minus action of this phi. Let us call them phi boundary of this phi boundary. So we need to solve this Laplace equation inside the disk. So a solution should look like this. It should be regular inside, so it is z over r to power n from n equals to 1 to infinity, or maybe from 0 to infinity. N plus to infinity z bar over r to power n phi minus n. So now integral of defined d bar phi boundary. So it equals to e to minus so this integral e to minus n z n minus 1 over Rn. I will only keep the terms which give a non-zero contribution. Z bar minus 1 over Rn is n squared. T to z. So it is some 2 pi RdR R2 minus 2 so n squared. So it is the vacuum function and vacuum functional, and well, we can also use the reality of phi to write it maybe as pi sum of phi n squared. Uh, so the wave function, vacuum wave functional for the free boson. So it is something. Well, now we can try to think what it means from the point of view of boundary conditions. Like, well, it disappeared, and no, it it does not depend on zero mode. It's like it's like a function of a particle with zero momentum. It's constant.
Zero energy components could matter when they go far away from the
Yes, well, the question is what we call zero energy. So, well, it's not quite zero energy. It's zero modes of harmonic oscillators. So this free field is a combination of harmonic oscillators corresponding to all modes, and this is the wave function of all these harmonic oscillators. And but but it has zero momentum for the center of mass. And if you want to so this is psi vacuum of phi boundary equals to this. But we can also compute, for example, we can try to add here exponential operator at infinity.
But this amounts to fix an actual function on boundary. Like,
What do you mean?
I mean, I could have expected the vacuum to shift in its interspace. But here, basically, what you introduce is just like the expression of a vector without the insertion of any operator.
Yes.
Yes, but my point is like, how do you represent the bra of the cat vacuum? I mean, I don't think this is the same.
Oh, right. Just apply this transformation z to 1 over z. And
this is whatever is for the bra, but that's not
yeah.
my point. My point is like the vacuum shouldn't like is not going to tell you any information about the function that you fix.
Okay. So the question, no. So no, the vacuum is the vacuum is a functional on the boundary values, right? Oh.
No, this like this what you compute is like the bracket of the vacuum with psi. The wave function is that is the bracket of psi with the vacuum.
No. What do you mean? Who is
A
psi?
wave function I can always write as the bracket of I don't know x with psi, right?
So it's kind of the analog of x is phi, like states,
Yes.
which yes, and it is this one. So it is kind of mm, I don't know how to write it. It's maybe
Psi scalar
phi.
okay.
Well,
Yeah,
they're
sure.
real, so it's the same. Mm. Oh, but by the way, going back to original question, like what uh, conditions at infinity should we take? So, but actually, we can also try to think in these terms about conditions for phi at infinity. Uh, Namely, here we considered this problem where phi was defined inside this disk. But we can do the same for the external of the disk and think what boundary conditions we should impose. So this is 1, this is 2. So it's kind of 0. say infinity. We can think which conditions we should put at infinity to make this problem well defined. And it seems to be obvious that if we consider the expansion in the inverse powers of z, then it will be equivalent computation. So in this case, phi equals to sum from n equals to 0 to infinity r to power r over z bar to power n phi n b plus sum from n to 1 to infinity r over z to power n phi minus n b. And psi vacuum maybe it's a kind of dual vacuum, but it will be given by the same expression. It equals to e to minus integral d to z, and here we again write these derivatives. Now it will be, yeah. So it will be minus minus n squared r to power 2n over z bar z to n plus 1. Phi n b phi minus n b. So, well, and I think it's more or less obvious that these integrals are convergent from n to 1 to infinity. These integrals are convergent and will equal to the same expression, right? So, yes, yes. So it again equals to minus pi sum from n equals to 1 to infinity n pi n squared with the vacuum wave function. So the answer, so I think the answer to a question about boundary conditions in that we should integrate over all phi's without any restriction. The only restriction is that they don't blow up at infinity. They can be constant, and we should integrate in this constant, and that's all. And this integration in constant, as we remember, will give a delta function, which is a conservation law for U1 charges. So remember that a correlator of exponentials, I alpha 1, phi 1, and so on, I phi of z1, e to I alpha n phi of zn, is proportional to delta function. Well, I don't know how. If we naively compute this path integral, it should be delta function of just sum times product of zi minus j alpha j times complex conjugate. And by the way, so we have this wave function, but it's also easy to see what happens if we put a vertex operator in the center of the disk, or at some other point. So this is psi vacuum. But we can also compute psi. We can also compute this state, like scalar product of vacuum e to the alpha 1 phi of z1 and so on e to alpha n phi of zn. This state with phi. It will equal to psi vacuum times times this phi. Maybe we need some notation for this. Phi, let us call it phi classical, times e to some phi classical of zi. So it will be some exponential, and in particular, yeah, maybe it's better to well, maybe it's better to write this product in the other way. And in particular, if we consider this this scalar product, when we have I alpha phi of 0 acting on a vacuum, which is the same as the state phi alpha, this state. So if we now look at this formula for phi classical, we see that when we put z equals to 0, the only one term survives, which survives phi 0, right? So this product, let me check recording. So this product equals to what? It equals to e to the I alpha phi 0 minus pi sum of n absolute value phi n squared. So so it means that this operator with charge alpha creates the wave function, which is the wave function of a free particle with momentum alpha. And it is natural because this phi is kind of coordinate in the target space, and shift of phi is a translation in the target space, and eigenvalue of translation is alpha, so alpha is momentum. So now this there is such a functional. Mm. Hmm? Well, I mean that. So maybe it's better to write it like this. So it's state. So, it is coordinate representation of this wave function of wave functional. Yeah.
Yeah, sure, but I mean, with psi n, you mean the Fourier components of psi boundary?
Yes. Sorry, probably I had to put, yeah, I had to put it everywhere. So it is phi boundary, and here it's phi boundary. And also, we can see here how this OP of the exponentials with vacuum works. So each of this wave function with the insertion of exponentials equals to uh, uh, to psi vacuum times exponential of this classical. And now we are free to expand this in powers of z and powers of z bar, and it will give a series in z and z bar of functions phi vacuum times some power of phi n, some power of phi minus n. So it's kind of coordinate representation of the OP. Well, maybe maybe that's all for today and for this week. So, are there any questions about what's going on? By the way, if someone wants, we can also compute this correlator of this exponential operators using this using this wave functionals because we have vacuum, we have some wave functional, and we can just multiply them and integrate in all Fourier modes. So in this case, it's computable. Okay, so any questions? Hmm? What do you mean by represent? So, oh, no. So do you call BPZ the equation with insertion of energy momentum tensor, or what? Mm. Okay, just some observation about the behavior of two-point functions. So, mm. So any other questions? Or okay, so thanks for your attention.